to refer?
Yeah, sure.
Yeah. Yeah, okay, I take it first. One more, can I have your smile a little bit? Okay, you want to take a picture with them?
If they don't mind.
You don't mind?
No privacy issues.
Okay.
Yeah, sure.
我幫你哋影啦，你影我呢個部分，你去曬度。
Okay. Okay.
可以拍過去。
賣廣告先。係啊。
好，拍埋。
You will need the renderer and you will need the sandbox. But I just want to emphasize that there are two distinct problems. So normally when we start exploring browsers, we first want to focus on the renderer side, because obviously at first you need to get into the target, and then after you have the code execution in the renderer, you can start attacking the sandbox. So this is kind of logical. And this slide represents basic idea of attack surface inside the renderer. There is a lot of code which is responsible for parsing different technologies that help to demonstrate a web page. Most notable components in this are the document object model, is the high-level C++ code, which consists of classes which represent the internal structure of the web page. There is HTML parsing. There are also various parsers of graphic formats, audio formats, PDF, XML, and so on. And of course, there is the JavaScript engine. Now, out of all of this, why do we want to focus on JavaScript engine? It is probably not the largest quantitatively attack surface inside the renderer, but it is the most complex and dynamic attack surface, which is relatively easy to fuzz and which always has some changes introducing new vulnerabilities. This is, I think, so there are two important points. Why do we want to attack JavaScript engine? First is that it is always complex enough to have vulnerabilities. It is almost impossible to make it completely resilient. And the second point is that it's always dynamically moving. New versions of ECMAScript will be developed and new features will be introduced, so that when new code is added, new functionality is added, new vulnerabilities can be found. But at the same time, JavaScript engine is very tricky target, very hard to attack. And among of different JavaScript engines that you can consider, Mozilla has SpiderMonkey, WebKit has JSC, Chromium has V8. V8 is probably the hardest. It is very strongly secured. It is also very quickly moving in its development. And the developers of V8 pay a lot of attention to security and hardening. If there is any vulnerability found, you can immediately see new commits that's related to patching the entire vulnerability class and introducing new mitigations for the exploit in many, many tires. So they really take it seriously, which is why V8 is I think it's like the frontier of the whole JavaScript engines for browsers. So this is the reason why I decided to focus here. Generally, there are two approaches to learning. One approach is start with the simple things and build up brick by brick your knowledge. Start with something basic, then build it up a little bit, and so on. And the second approach is dive immediately into something as complex as possible. I think it's individual which approach is good for you, because we are all different, and what works for one person doesn't work for another. So for me, the second approach always works better, which is why in my approach to study, I take the hardest target of all the possible that I can find. I learn to attack it, and while my failure rate will be higher than if I attack something simpler, but also I learn much faster, and the skills that I learn in this way can be backwards ported to the more simple targets. So this is the approach that you can also try. That's the reason why we're talking about V8 today, and especially investigating the entire process starting from zero. So the first thing you need is to set up the research platform. Normally, if you're just getting started, some people try to test vulnerabilities on publicly available build of the software, which is a big mistake. So for example, you have some exploit and you try to test it on the Google Chrome that you have installed in the system. This is definitely not a good idea for many reasons. You always try to build a good research platform, which includes code checkout in a convenient IDE. You need to build the system, including debug symbols. You need to have several different builds, which I will explain a bit later. The release build, debug build. There should be a separate build for fuzzing. because fuzzing requires special optimizations and special configuration of symbolic information included. For example, you cannot do fuzzing with a debug build because it's too slow, and normally you don't want to fuzz with a release build because there is not enough introspections in place to catch some possible crash. So you need a special fuzzing build. And fuzzing build would be also helpful in reproducing the vulnerability, while debugging build is usually helpful in the initial investigation phase. So I'm going to show you how to approach V8 starting from 0. First I'm going to, so there is actually for Google, there are very comprehensive documentations available on how to build everything. And there is nothing complicated about building V8. There is document building V8 from source, I think. So there is this document, you can find it. Basically, there are two things that you need to know about the Google ecosystem for building. First, they have their own build wrapper infrastructure, which is related to gclient, short for Google Client. The basic idea is that when you build complex projects such as Chromium or V8, they have a lot of third-party dependencies. And when you check out to a different branch or a different commit, you also need to change the dependencies, the commits in their respective dependencies. So what gclient does is it automates this process. And it automatically, when you execute gclient sync, it will automatically synchronize all the third-party repos inside the main repo so that they will be the exact known version. Similarly, it will fetch the project, Google project that you need. And this is the first thing. Another thing is that underneath Google ecosystem for building uses Ninja. That's a very familiar workflow. First, you will have to execute gen name of the build to generate config files, and then you execute Ninja build. But actually, Google provides us for V8 with a convenience helper, which is named gm.py script. It's a Python script which wraps the Ninja logic. And with this script, the building is very straightforward. You just execute it, and you give it the name of the either release or debug, or there are different versions of build that you can accomplish. So basically, you just tell it what you want, and it builds it. After you have built it, the output will be in the out directory in V8. So this is my V8 repo. This is already checked out. Need to make the slides a bit visible. So this is the bare bones idea of how to build V8. Another thing that I didn't mention is you will need to install the dependencies, but it's also very straightforward. It is included here in this different link named Checking Out the V8 Source Code. They have a dedicated script to install dependencies which are required for building it. So there is this one. The install build deps script, Esage, will just fetch and install all the third-party packages that are required to build it. So there is nothing complex. Another thing that you need to remember, every time when you change to a different branch or a different commit, normally you can do it with Git. So currently I am already on the specific commit. This is a bit different commit that I gave to you because I just realized that my own debug patching logic was based on a different commit. I just realized it today, so it has to be a bit different. This is the pre-patch commit for this vulnerability. And you can do git checkout commit number in order to switch to a specific commit of vulnerability, which I will show you later how to find it. And after you did the checkout, you need to do the clean sync again, each time, because all the third-party dependencies, they have to be synchronized. And then you build it in the same way with either GMPy's helper script or with Ninja directly. This is the basics. A few words about the differences between the release and debug build. Normally, in different code bases, debug build has several distinctive differences from the release build. First, it has additional debug logic, debug logging, which helps to know what's going on in the program while it's running. Second, it has additional checks, which are usually named asserts. The asserts that are present only in the debug build and they are not present in the release build. This is very important because sometimes they can hint us at the vulnerability. And a third thing about debug builds, normally they have full symbolic information included, but this can differ from project to project. And fourth thing is that debug build usually is optimized for GDB debugging. You know that in GDB, depends on the level of optimization, you may be unable to inspect local variables if the code is optimized. Normally, a debug build provides a low level of optimization to the code so that you can actually inspect the local variables, you can single step, put a breakpoint and do everything else. But this is not guaranteed actually. In some projects, even if you build a debug build and you try to debug it in GDB and you cannot inspect local variables, so you have to tweak something. And when we need to tweak something, we need to go deeper into the configuration and change some settings. This is a bit advanced topic. Another thing that you need to know is how to use debugging. This is very straightforward. After you have built V8, you simply attach to it with GDB and you can put some breakpoints in the source code. There is nothing very special about it. And another thing that I want to mention about building, a few words about the special config actually. So there is a configuration file in V8 build which configures which exactly functionalities are included or excluded. And this is a very interesting file. I think it's going to be build.gen. In the root. So in this build.gen, it's a configuration file for the build which configures the entire project. And then there are similar files included in the subdirectories which configure a specific config of that particular piece of project. So this top level build.gen is very important. Especially here you can find configurations like variables starting with V8 enable. Actually, it's possible to pass this in the runtime when you're building. Now I just want to show you that there is many interesting flags that you can enable. There is some verifications. You can inspect it later. Many of these additional advanced features are actually quite useful for introspection and research. Especially for my demonstration, I enabled the flag V8 enable tracing, trace ignition, and V8 enable trace baseline exec to enable some low-level tracing functionality. Now this is kind of homework. You can inspect this file and maybe find something interesting. If you want to build in some advanced features. So your research platform consists of code checkout with convenient ID, second, release build, third, a debug build of the program with all symbolic information, and fourth, the ability to debug. You can attach the debugger and put a breakpoint on some source code level, ideally. When you have this kind of research platform, you can move forward to testing, because now you're empowered and you will not be held back by some limitations of the release grade software. Now we're going towards the patch analysis. Patch analysis consists also of multiple steps that I'm going to show you, and feel free to follow what I do and try to come up with your own ideas, maybe how you could do something better or investigate something in the process. Normally, Google publishes its security advisories in the blog named Chrome. Where is it? Chrome releases. So I'm going to search for a specific vulnerability now that we're interested in. Chrome releases is a blog in which they publish all the updates, and here also will be released information about vulnerabilities identified, which is very useful. In this blog, it includes both Chromium and Chrome OS for different platforms. For Chromium specifically, we are mostly interested in the stable updates and desktop updates. And you can see here, for example, from November 12th, is just a couple days ago, there is an example of how it looks like. Multiple vulnerabilities here listed. And it also includes a link to an issue in the bug tracker, which is currently closed, because Google normally will keep freshly patched security issues closed for at least 3 months. And for actively exploited 0 days, they can close it for 6 months and even more. So currently you will see something like this, access denied. And at some point it will be disclosed. So while you see all these vulnerabilities, it is not straightforward to analyze them, and you will need to analyze the patch. Now I'm going to show you how you can go from here to patch analysis. Just need to plug in my laptop.
Special. What are you to see? This is a new version.
Hai ông cô Universe cũng kết tổ rồi.
Should be good then. Okay. Next, yeah. Yeah, he scanned.
Okay, great.
Is it good? Yeah. Right.
Yeah, it's working. Thank you. Okay, so when this kind of patches come out, we want to analyze the vulnerability, but the issue is not available. Of course, the issue is most interesting to us in the bug tracker because it has all the information. It has the description, it probably has the POC, it has the discussion of developers, which can provide valuable hints. But currently, when it's just released, the issue is not available and we need to proceed to analysis of the patches. So how can we find the patch from this page? I'm going to go back to this specific vulnerability. It was a 0-day attacked in the end of the 2022, around November. It was exploited in the wild. It was caught by Clemently Singh of Google's threat analysis group. This issue was created. Initially, when I analyzed this vulnerability, the issue was closed. So we need to find the patches. There are two ways how to identify the patches for this bug when the issue is closed. First way is here at the top of the blog, there is available a patch log for this release. Normally for the Chromium release, this patch log will be huge, but currently, because this was an emergency patch, there would be only a few patches here, as you can see. Basically, dependencies, change of dependencies, increment in version, and the actual patch for the vulnerability, which is this. And here we actually what's going on here, it says role V8. It means that it includes the updates from the V8 repo. So we can pick this link, which points to the V8 repo, and go to the patch. So inside this patch there is also a version update, and here is the link to the actual patch. Now inside the patch you can immediately notice very interesting information included inside of the description. It can provide multiple hints at what is going on with the vulnerability and where to look for. This is the first way to find the patch. From here you can click diff, and you can see the diff in a line which is formatted in a linear fashion. It's actually diff side by side is a little bit more convenient for manual analysis, but this kind of diff is also helpful in some situations. Now, another way to identify the commit for a specific vulnerability is go to the Chromium review. Where is it? Chromium review. This is a place where Chromium patches get reviewed. And here we need V8 repo. V8/V8. And I click view changes. So now what we want is we want to mention, to notice the number of issue that was included in the security advisory. This issue might be access denied, but we can actually put it here with bug specifier. Search for the bug number and you can find the specific patches that correspond to this issue. And you can see that there is actually multiple patches that are basically the same. It's because they target different branches. There is the main branch, there is a specific Chromium branch, and then there is also an interesting commit on the upper side, which is related to systematic mitigation of this kind of vulnerability. Specifically, there is some Samuel Gross added some additional configurations to fuzzing in order to try and find more of this kind of vulnerabilities. This illustrates what I said before about Google's approach to security, that they react very quickly to vulnerabilities and try to move proactively and try to mitigate the bugs as fast as possible. This is not included in the workshop, you can investigate it later. So if you click on this review here, you can actually click in expand all and you can see a side-by-side view of the patch. This one is better suited for manual analysis. So now I'm looking at the patch, and the goal is to eventually to create a proof of concept. But first, of course, I need to understand what is the vulnerability here, what is going on here. So if you look at this patch, it is quite large, and everything in the patch is actually related to the vulnerability. It's not some random code. And the thing about JavaScript engine patches is that it is very hard to identify the root cause from the patch. Normally, if you look at security patches for easier type of bugs like buffer overflow, you can immediately spot some pattern of memory corruption. Like you can see that there is some memcopy patched, there is some additional logic check added. But in JavaScript engine patches, normally you can see something that looks like a lot of refactoring, and it's absolutely not clear what is going on here and how can this possibly be a security issue, and this is normal. So how do you approach it? The best way is to have as much contextual information as possible. You need to be familiar with JavaScript engine, and currently there doesn't exist a singular source that you can learn everything possible about the internals. Even the ECMAScript specification, it only defines the high-level aspects of the runtime. And for example, if we talk about optimization, there is no specification for JavaScript engine optimization. Basically, each engine developer invents their own approach. And which means that you will need to analyze information from different sources in order to build up the context to know a little bit how JavaScript engines work. So I will, for example, show how I approached this patch, where at the moment when I analyzed it, there was no proof of concept available on the patch, and the issue was still restricted. So by looking at the patch, generally it didn't make sense to me, but there were a few things that stand out. So the first thing I noticed is that somehow it's related to scopes. There is a lot of discussion about the scopes. Then I noticed that it is somehow related to eval, because there are some variables that check something related to eval. And these are the first things that I noticed. But then from here it's not exactly clear. So how do we go about it? Eval you probably are familiar with. Let's assume that you are not familiar with anything. Basically, the idea is that you start picking out concepts that you're not familiar with and you research them. You can, for example, you can research them on the internet, or you can ask ChatGPT about it. But if you ask ChatGPT, then of course you should be able to validate it independently to exclude any hallucinations. So assuming that probably you are familiar with eval, eval is a JavaScript built-in which takes in a string and executes its JavaScript code. And scope, for me, I was familiar with the concept of scope, which is a concept from programming theory and compiler theory. Especially the scope is, so, okay, let's ask ChatGPT, what is a scope? Explain scope in the context of programming theory. So here, is it close enough? Scope is a particular region of the program in which a specific variable or identifiers are valid and can be addressed. So there can be a function scope, there can be a global scope, there can be scopes that are artificially defined if you put some braces, and there can be some other scopes inside the for loops or something like that. So this one is familiar. With that knowledge in mind, I still keep investigating the patch and picking out every concept that I'm still not familiar with. For example, okay, now I know what is scope, I know what is eval, and then I noticed that there is a lot of things going on around sloppy eval. What is sloppy? And it turns out that sloppy is the mode of JavaScript engine execution which is opposite to strict. A strict mode, so normally all JavaScript executes in sloppy mode, except that we don't usually call it like sloppy, it's just normal mode. And then there is another mode which is called strict, when you put use strict in quotes in the beginning of the module, and it will be executed in slightly more hardened, with slightly harder rules, and with some additional checks and with some additional internal differences. This is defined in ECMAScript specification. So there is sloppiness, So basically, this is the first step of analyzing a JavaScript engine patch. You make sure that you understand every concept that you see mentioned inside the patch. And after you read everything related to that concept, you start reading the patch again and try to put it together in your mind and make some hypothesis of how it works. Regarding patch analysis, there are two levels on which you can analyze the patch, the high level and the low level. On the low level, you want to understand what actually causes memory corruption or state corruption. In a very ideal scenario, if you have some basic buffer overflow, normally you would see a pattern like memcopy or maybe an integer overflow and further down addressing of some buffer out of range or something like that. Basically, you will see a pattern and you know, okay, this is memory corruption. So at the low level, you understand the vulnerability in the patch. But also, there is a high-level context of the patch analysis, which is what is actually going on here? Which is what is this code responsible for? What kind of data flows here? How can I reach it? What kind of technology does it implement? This is the high-level context which is required for you to build a proof of concept. So the thing about JavaScript engines is that normally when analyzing patches for simpler software, we start with the low level. So we try to find the specific memory corruption point, some pattern that we know this is probably the vulnerability. But for JavaScript engines, this is not possible. So we start usually with a high-level concept. We start investigating the patch and building up the mental model of what is going on here, which technologies are involved, and so on. And I want to emphasize that the more you know about JavaScript engines and compilers, the easier it will be to understand it. But also, even if you already know a lot about JavaScript engine, in most cases you will still need to research further, because most of the vulnerabilities that I've seen always consist something new. And it's not like you learned and you just understand everything. You will still need to do this research step. So after doing all this, I have the different pieces of knowledge, and I start hypothesizing and building a mental model of what is going on in this patch. And I think so this seems to be related to how evil is processed specifically in sloppy versus strict mode. This is somehow related to handling some internal variables inside of scopes. Another thing that I didn't mention yet is there is a comment that talks about arrow function here, and there's another. So actually arrow functions are mentioned here a lot. So obviously this has to be related with arrow functions as well. We can read up about arrow function or ask ChatGPT. So here is, actually ChatGPT is quite good in this kind of tasks. When you know that this information is contained in specifications and in many blogs on the internet. So ChatGPT is probably highly correct about this. There is not much hallucinating here, as opposed to when you try to ask it some less common question. So there is a definition of arrow functions. When I researched it, I found MDN docs to be helpful, which MDN web docs from Mozilla. They have a lot of information about all aspects of JavaScript. So basically, arrow function, it looks like this. It's a simplified function expression. When you don't write the function token, but instead you use a parenthesis and you use arrow followed by expression. There are several formats that you can use it. And regarding the sloppy evil, when I started researching this, also I did some basic research. And There was one blog that was quite helpful that attracted my attention. It was this one, Duality. What's up with sloppy evil? Why it can be an issue? And here it's the explanation that is very relevant. Is that when evil is executed in sloppy mode or normal JavaScript mode, it can actually create and access variables outside of the evil scope. So this is our evil scope. Inside of the string, it's created a separate scope for addressing variables. But when evil is executed in normal mode, it can actually access variables outside here. But if evil is executed in strict mode, it will only reference the variables inside of its own scope. It cannot go to the global scope or the surrounding scope. And this distinction, it immediately clicked with me because I realized that this must be the nature of the vulnerability. Clearly, this is something related to it. So after this kind of, you collect information from different sources bit by bit, you let it process in your mind and build a mental model of what can this possibly be about. So I was reasoning something like this. Okay, so there seems to be some sort of inconsistency between processing evil in strict mode and in sloppy mode. And it is related to processing of arrow functions. And probably it is related to arrow function because arrow function would have its own scope. So probably evil has to sit inside of its scope, and somehow when there is an inconsistency, there would be a type confusion. So this is a kind of high-level thinking that can be applied here. Of course, I will read in details every function that is involved in this patch. So, for example, from specifically investigating the patch and reading it, we can deduce that V8, in order to handle this situation, that evil has different internal semantics related to whether it is in strict mode or in sloppy mode. So V8 internally tracks evil calls, it records it, in order to keep track of where exactly evil is located and in which mode it executes. So I kind of built this general understanding of vulnerability. You can analyze the patch and get some more details about it. There are some flags involved, which seem to set how exactly specific further internal compilation will be processed depending on the evil mode and so on. So after I built this mental model, at some point I just stuck, and I realized that now I need to go to the testing. I kind of hit the limits of the theoretical analysis, and I know that next thing is I need to try to test something. But another thing that I want to do with this patch is actually try to narrow it down to the actual vulnerability. Try to pick out one strong indicator of memory corruption or state corruption. So this is a question for you. Take a look at the patch and try to identify the indicator of the vulnerability. Something like memory corruption, but it's not here. Something that you think, okay, this is it. This is very relevant. This is probably this function that is vulnerable.
Scope CC.
So normally in a simpler patch, we would look something like memcopy or array with an index which is calculating or something like that, that you see that, okay, this is it, this is the memory corruption. But here it's a little bit more complex. But still we can try.
Mm.
Anything stands out?
Checks.
Checks. Yes, that's it. So this is the correct answer. First off, we will be looking at the right side, which is the code that was added. Our assumption is that because obviously this code is patching the vulnerability, so our main focus will be on the right side. Some of this code must be patching the vulnerability, and some of the functions may be more relevant than the other. So this point actually attracted my attention. Inside of the function named record declaration scope eval call, there is a check. So the thing about the checks in Chromium code base is that this is not a debug check, it's a release check. And what it does is it immediately crashes the browser. And you know that software developers are very serious about crashing anything, and they will never ever allow to crash the browser unless there is a very serious reason behind that. So in Chromium code base, check is a release check which is normally added when there is such a bad condition that we just need to crash. And I mean, it's just crash, of course, there is no state corruption or anything, it's just a check. And this immediately tells us that, okay, this is the relevant part, let's look deeper into it. So when I realized this, I started looking deeper into what exactly does it check, and it checks that the language mode is sloppy. And once again, we go to investigate about the sloppiness, and we analyze the context from which this function is called, and so on. But at some point, the theoretical analysis becomes just too complicated, and it's just easier to do some tests on the research platform. Also, before I go to practical tests to try and reproduce the bug, the next stage is to, after we have built the mental models of what is going on here, we can list the prerequisites of the POC. So at least hypothetically, if I didn't know what's going on here, I know that probably I will need some JavaScript code which has a mix of strict and strict and sloppy mode. First, it will need to have eval, and probably that eval has to be located inside the error function. This kind of prerequisites that I need to put. And once I have these prerequisites, I start building a hypothesis of how exactly to put these prerequisites together to write a specific code to reach this vulnerability. At this point, there will be more tests, and actually this bug is extremely complex to reproduce in this way. If you're just looking at the patch, I think none of those people who analyzed the patch were able to actually create a reproducer, because it's just insane. But actually this is what we normally do, and I think it is possible with enough experience, even with this kind of very, very complex bugs, to create a proof of concept. For our tests of proof of concept, we will take a public proof of concept. Now, going back to the advisory, we can now open the issue, which is currently open because a lot of time has passed. So the issue is currently opened, and it has an interesting proof of concept inside. Now, I want to emphasize that this stage, proof of concept dynamic tests, it's the same in many situations. Whether you created the POC yourself, whether you took it from the internet, or took it from the issue, or took it out from the 0-day, or even if you fuzzed your own engine, did some fuzzing, this would be crash triage. Basically, it's the same process for all these cases. So in this situation, we will be working with a public POC. Obviously, when we start approaching the POC, we will need to read the issue, because there is likely to be a lot of interesting information in the comments. And currently I'm going to skip this, but you will be interested to do it later. I just, by quickly going through it, I see that there is another POC here. It doesn't look much better to me, but it might be also useful to test it. And another thing interesting in this issue is that we have a show of specific debug check that was produced by this proof of concept. So we need to take out this proof of concept and start testing with our V8 build. But actually, it's a bit cold here. So once again, I want to show that we will try to use theoretical analysis even at this stage as much as possible. The first thing I do is I want to look at this POC and make sure that I understand everything, make sense of it, and then I will try to minimize it. Now I will open the POC in my IDE. And this is the same proof of concept. And I want to introduce you to the skill of looking at the exploit from a like an artificial intelligence, I would say. So normally when you see the exploit or proof of concept, what do? Probably you will read it line by line. If you're like most people, if you're like most of my students, that's what they try to do. Reading everything and trying to understand this. If the POC is small, it works. But sometimes you want to save time, or sometimes the exploit is very large. So basically you try to see it as a whole picture, and then you break it down in pieces that you can immediately recognize. For example, looking at this POC, first of course I noticed that there is an interesting comment, bytecode old age. And of course I will go and research what it does. When you're investigating a vulnerability, every bit of information is valuable. If you notice something that doesn't make sense, go and research it. You can look it up in the code base, you can look it up on the internet or ask ChatGPT. And sometimes this kind of tiny detail that you can look up, it actually makes the difference between solving the problem and not able to solve the problem. So anyway, I noticed this, and of course I will go to research it. I will talk about it later. The second thing that I notice here is that this function A is a custom garbage collector implementation. This is something very familiar to me because I attacked a lot of JavaScript engines, and garbage collection is a very important element of a typical JavaScript exploit. Because JavaScript engines use automatic memory management, where objects are allocated and freed using some very complex internal heuristics. And garbage collector is a special algorithm which usually is very, very complex, that goes through all the objects that are currently available on the heap and decides whether they are still alive or not. When it's not alive, it frees them. If it's still alive, it can mark them to promote them to another space for long-living objects or something like that. And in all modern JavaScript engines, garbage collection is very, very complex. And quite a few vulnerabilities in JavaScript engine were related to triggering of garbage collection. And in order to trigger it, what you do is, so normally garbage collection is, in JavaScript engines, is governed by internal heuristics that you cannot control directly as a JavaScript developer. You cannot tell the engine, please go and collect the dead objects for me. Normally it is fully automated and you do not have control over it. But you can kind of trick the engine into doing the garbage collection by allocating a lot of objects or a lot of data. This is what this piece of code does. It allocates several very large array buffers. Basically it works like a plunge. It allocates a lot of memory and pushes out, it creates a low memory situation, so the garbage collector will kick in and start processing the objects to see what can be freed, because we need more memory. And this trick actually works in all engines, not just in V8, although it may depend how exactly it can be implemented, because, for example, when you allocate an array, normally it may or may not allocate the backend storage immediately. So this is not guaranteed. Now in this situation apparently it does, but in some other engine it may not. And even if you try to allocate a large array, it can simply reserve some small space first, but without allocating it. So it can be a little bit different. The same garbage collector implementation can be also done with different ways, not just array buffer. Obviously it can be large strings, it can be a large amount of some other objects or something like that. Okay, so this is just garbage collection. Moving further, there is a loop of just 13 iterations. Inside the loop there is a function, and then there is an arrow function expression. Here is it, especially the form with a default argument. You can go to MDN to it doesn't show the default argument, so basically you can set a default the value of the argument by default in the parentheses here, which is what happens here. So obviously this is an arrow expression. It defines a function in place, then it immediately executes it. Inside the function there is something messy going on. It's absolutely not clear. There is a class defined. There are some class members and to each class member assigned an eval. And there is the same function called with eval, and then there is a ternary operator also here. Ternary operator should be familiar to you. It's a special conditional operator which has 3 branches instead of 2. It looks like question mark and a colon. So the first part is a condition, the second part is the branch which executes if condition is true, and the last part is the branch which executes if condition is false. And then there is one check. In a particular part, in a particular point of the loop, we invoke a garbage collection. Okay. So after looking at the POC like this, I try to think, what can this possibly mean, especially if that I already looked at the patch, and I already know that this is related to eval. The class immediately stands out here because turns out that classes execute in strict mode always in JavaScript. This is defined in the specification. Maybe this may not be very familiar if you're not a JavaScript developer, but you can, during this kind of research process, you can find it out. And then also, so after analyzing this, it still doesn't make a lot of sense to me, but this part about old age once again attracts my attention. And if you go and research, look up in the code base, it turns out that in V8 there is a mechanism of flushing old bytecode. So every time when a function is compiled, it generates a bytecode, and if the function isn't used for some time, then during the next garbage collection cycle, the bytecode will be flushed, and basically it will be freed. And the next time when the function is accessed, the bytecode will be generated again. It's a kind of mechanism that helps to optimize the engines to save memory by freeing those bytecode parts that are not available. So after analyzing the POC like this, I'm still interested in simplifying it a little bit, because when you debug a test case, you always want it to be as simple as possible. Normally, fuzzy test cases are very large, and the problem with that is that you cannot identify which specifically part of the test case is related to a specific situation in your code, which specific part will trigger a bug or cause something. So normally you always want to minimize the test case as much as possible. After some tests, I will show you my own minimized proof of concept that I achieved. So this is the minimum, the smallest that I could achieve. You can see it's also a little bit cleaned up. So the first thing that I do here is I replaced the garbage collection with intrinsic, which is exported by V8 GC. It will require a special command line flag that I will show you later. Normally, this GC is not available in the browser or in the production environment. It is only available when V8 runtime is invoked with a special flag. So I replaced it for readability, then I simplified the internal part. Basically, there is just one class member now with 2 evils. Normally, you can do this kind of minimization manually, but you can also automate it. Usually it can be done by some sort of ultra specialized fuzzing when you have a large proof of concept like this, and you generally understand what's going on here, which pieces are absolutely necessary. You can write a specialized fuzzer that can mutate different parts while keeping it along the same conceptual base, and eventually some of it may work. So one reason for generating a minimized test case is to simplify your understanding, to optimize your research work. And another reason is that sometimes different test case may produce a different crash inside, which is also very useful. This is what happened in this case, as we will see later. And when you have a different crash site, it provides you with additional information for analysis. Now let's go to our V8 build and try to analyze the POC. I'm going to try the release build first. D8 is the name of the JavaScript runtime, which you can invoke from the command line. If you just run it, it will open a REPL prompt where you can generate some JavaScript, you can execute something, or alternatively you can invoke it with your POC and try to achieve a crash. Now, I'm going to test the original test case that was provided by Google in the issue. So you can see here that I'm testing in release build and it doesn't do anything. This is totally normal. In the release build, proof of concept may or may not work. The thing to understand, this is why it is so important when you do fuzzing is to always fuzz in a special build, not in the release build. Because in the release build, the bug, well, it does happen underneath, the bug is still there, the trigger is still there, but maybe the memory corruption is not triggered. I think, I'm not sure, maybe, actually we can try with the flag. Because in the debug, the flag actually is not necessary, but here it may be necessary for the release build. No, still doesn't work. So we'll need debug build for that. Okay, so here is our crash. It shows only on the debug build. Now take a moment to process what's going on. As I said before, a release build may not show you anything if you run the exploit. And normally, so this is the reason why normally we want to use debug builds, And especially we want to even go deeper into the configuration and try to tweak the debug build in such a way that it is even more sensitive to any kind of state corruption or anything that goes wrong. Currently, V8 is already quite sensitive. There are a lot of asserts in place in the debug build, and there is a check here. It is the same type of check which we saw in the Google issue. And also you can notice here that I didn't use the flag bytecode old age. So, because apparently it still does use it underneath, and it happens automatically. Now I want to show you what happens if I launch my minimal pop. First off, it cannot find the GC implementation, GC intrinsic. This is because we need to provide a special command line flag which goes like expose GC. Okay, now garbage collector is found, but the proof of concept doesn't give us anything. It requires a special flag. Okay, it will require a special flag, so for now we will leave it here. And I want to show you another thing, which is if you launch D8 with ---- help argument, you will see all the possible arguments that it can accept. Now you can see it's quite a huge list. Very, very long list of all sorts of arguments. All these flags, they change different aspects of V8 configuration. And many of them, for example, are related to tracing or debugging, introspection. They're very, very useful for analysis. Even sometimes you don't need to attach a debugger, you just use some of these flags and you are able to see what is going on inside of the engine. For example, if you grab the output with something like tracing, you can see all the different flags that can trace something that goes on with the code. You can see that there is like a huge list of flags related to just tracing alone. Trace protector invalidation, trace block coverage, tracing ignition codeagen. Basically everything that goes on inside the engine, you can trace it at the runtime. This is very, very convenient. Another thing that I just grabbed bytecode, and there is also quite a few interesting flags related to bytecode. For example, you can see there is a command line argument ---- print bytecode that will print the bytecode of your function. And here is our familiar flag that we already saw in the POC, the bytecode old age. And here it shows that it takes as an argument the number of garbage collections before flushing the code. And default is 5. This is also the next one, ---- trace flush bytecode. Very useful, because we already know that this POC has something to do with bytecode flushing. So obviously, this will be useful. Another thing that you can find is tracing garbage collection. If you grab it, for example, you can use GC verbose flag, which will make the garbage collector report what it does in a more verbose way. Another interesting flag is related to stressing anything. Stressing, because JavaScript engine is a very delicate mechanism, which internally it relies on a lot of heuristics, which trigger when some conditions are met. So, and when the JavaScript engine executes, there is a balance between these heuristics. So, in order to facilitate testing, such as fast testing, we can actually apply pressure to these heuristics and make them trigger in more aggressive way than they would normally do if just executed normally. So there's quite a few this kind of stressing flags. They are probably used internally by Google during fuzzing and some kind of unit testing. Okay, this one flag is quite interesting. Stress flash code. Because we already know that we have an issue related to flashing bytecode, and there is a special flag to it. And I'm just going to run my previous minimized POC with it. Stress flash code. And we get a crash in a new call site, which is great. This is also a check, but it's a different one that we saw before. And this check, it will be very useful when we look deeper into the bug, because it shows us another place where the vulnerability can manifest itself. Especially here, we can see that there is a feedback vector length inconsistency reported as a check here, which immediately provides us with clues. But I haven't started to talk about feedback vectors yet, so it may not make sense yet. So my point here is that the proof of concepts and exploits are quite flaky, and you will need to test in different configurations and maybe with special flags. And also you will always want to achieve a crash at a different call site, because it greatly facilitates the analysis. It really provides information right away as to what is going on here. So how do I go about this? I'm going to come back to our original POC first. Here is the original crash. It's the same crash that we've seen in the Google repo. So when you see this kind of thing, the first thing to do is, of course, theory and research first. Before even starting the debugger, you want to make sure that you understand everything that is mentioned here. At this point, we apply the same technique that I showed before. Take every concept that you don't know yet and look it up. And now the problem is that if you try to research feedback vectors, for example, in the Google, when I tried to research it, it was not nowhere to be found in Google, because it's quite deep in the internals of V8. Nowadays, of course, you can find a few publications from our researchers who looked at this vulnerability, but before that, it was not available. So basically, you will need to go to the V8 repo and analyze the code to understand this kind of concept. Here, when I look at this output, what I didn't understand, so obviously there is a typecast, there is a type confusion here at a specific point. Expected property cell, but found a feedback cell. So I will need to research property cell, feedback cell. Old space is a familiar concept to me as a JavaScript engine researcher. It's related to memory management and garbage collection. Feedback vector, also I will need to look up in the code base. And everything else is pretty much irrelevant at this point. So how do you look it up? Go into the V8 code base. For example, class feedback vector. You will find the definition of the class. Here is it. And you will need to read read this definition and to understand what is going on here. So there is a feedback vector. Similarly, you can look up property cell, and what else is here? Feedback cell. Obviously, this kind of analysis will take quite a lot of time because you need to read the code and also you will need to internalize it to understand what is this. So I'm going to very briefly explain what is this. Feedback is related to to code and data specialization, because JavaScript engine has a universal type system. So if you declare a variable in JavaScript, it can be any type. Var A, and it can be a string, it can be an object, some small numeric value. And when you work with JavaScript, it's absolutely transparent. But the key property of JavaScript engine is it needs to optimize everything. And when it optimizes, it cannot rely on the same rich logic to investigate what kind of object we're dealing with. So normally, if the JavaScript engine executes in the interpreter phase, it will test an object in many ways, like is it an object, is it a string, is it maybe a numeric value, and then depending on these outcomes, it will proceed to a specific logic to execute the semantics in a specific way. But when JavaScript engine optimizes it, it doesn't want to test everything. It wants to know, okay, here is it is a small integer value for sure, and this is a string. And because it knows it's a string, it will apply at the low level. It will immediately apply the code which knows how to process the strings. But how can the engine know it? It turns out that during the runtime, when your program is executed, the engine will collect feedback from your program, and it will record which types are usually used. For example, you have a function that accepts some variables, some arguments, and normally the variables are universal type, but you call this function many times with an integer variable. And internally, the JavaScript engine learns that this is most likely will be an integer. And next time when you optimize the function, it will assume that it will be an integer. And it will apply just a little bit checks in the compiled code, in the optimized code, a very small check, whether or not the map of the object is consistent, and it will bail out if the assumptions are not met, and that's it. But the rest of the code is optimized. So the basic idea of the feedback is that the engine collects this kind of data during runtime, and it saves information internally about what types are usually used in each specific point in the program. Especially feedback vectors are specialized to bytecode level. So each bytecode has a specific piece of feedback related to it. And engine learns that this bytecode most probably will work with a heap object, and this bytecode will work with multiple objects. This is called polymorphism, and if it works with just one object, this will be called morphism. I'm just going to mention this. There is not much information about this kind of polymorphism and monomorphism. I want to find the blog that was helpful for me. This one blog, I think What's Up with Monomorphism, is quite comprehensive. It explains at a more or less high level how it works. Similarly, you can ask ChatGPT about this. So when JavaScript engine optimizes, it always strives for monomorphism because it is the best optimized case. If it knows that this particular object is always a string, then the optimized code will be specialized to it and it will be 100% optimized. But if it learns that this object sometimes it's a string and another times it's a heap object, then the feedback becomes polymorphic and it takes much more code to implement it, much more additional logic. Basically, it becomes less optimized. Eventually, if JavaScript engine learns that an object is completely arbitrary, then it's completely, it's the worst case scenario. With that background in mind, the feedback vectors are the specific data structures which store this kind of feedback. And now I just want to show you how it looks like before we started further tests. So here is a random example of feedback vectors. This file is a log from my tracing output. It has some additional debug logic inside of it. Basically, inside V8 you can print feedback vectors. There is a familiar debug print function that you can invoke as an intrinsic inside JavaScript, inside V8. And you can also invoke it inside the code itself. So this is how a feedback vector looks like. It is an array which is separated into slots. Each slot represents one bytecode, one opcode. And then in each slot there is a specific metadata related to that bytecode, which actually records what have we seen so far. So in this particular screen you can see that there are many uninitialized symbols here. It means that the feedback vector has already been initialized with the bytecodes. For example, there is slot 0 literal, slot 1 load global, LDR global bytecode, slot 3 is a call. So this is specific bytecodes, but the feedback inside of them is not initialized yet. It's still open. And a little bit below, and here you can already see that feedback has been initialized for slot number 3, for example. There is a weak pointer and there is a specific function. So basically the engine learned at this point that this particular call bytecode usually will call the eval function. And because it learned it, it can optimize it very well. If it generates a low-level code for it, then it just goes straight to the eval function without calculating some offsets or functions of something. Similarly, in this slot number 5, we can see that a map has appeared. A map is a specific layout of an object in V8, which identifies the offsets at which specific properties will be located. So here basically it identified a specific format of an object that would be most likely used in this bytecode. No, this is not exactly a bytecode, it's a type of feedback, but it's linked to the bytecode actually. So this is how feedback looks like. And how it works is that, as you have seen, when the bytecode is compiled, first the feedback object is allocated and the internals will be uninitialized first. And then it goes through it and it starts to collect feedback about which specifically objects are used, and these fields will be filled out. Now, the thing about feedbacks inside JS is that there are multiple classes that are linked together to implement this system. It's quite complex, so I'm not going to explain it here in detail. What you need to know is that the main entity is the feedback vector, is the large array that I showed here. The feedback vector, this is kind of visualized. It is divided into slots. Each slot represents one bytecode, and it stores the metadata related to the specific bytecode, the feedback from it. So one thing is the feedback vector, and another important class is the feedback metadata. And here even there is a helpful comment that feedback metadata is an array-like object with a slot count. Now, the most important thing to us to understand, there is the feedback vectors and feedback metadata are two most important structures in this system. So feedback vector stores the information about bytecode. It's divided into slots. Each slot will contain a bytecode. And metadata, on the other hand, it is related on the specific feedback that was collected about these bytecodes. And it is very important for this vulnerability to understand that these are two distinct things. Now, I'm going to go on with the analyzing and debugging our POC. What else can we learn here? we can go, of course, we need to investigate this crash point, specifically in this accessor assembler file, to get an idea of what is going on. So this is our crashing point, and I want to quickly understand what is going on here. First off, what you need to know is accessor assembler is a special code in V8 which builds low-level primitives for when it starts lowering interpreted JavaScript into lower level. It uses this code accessor assembler. So it is not possible to put a breakpoint here. In the actual JavaScript engine, it will just generate some assembly code, and so this internal code will actually be implemented inside of the binary code. And for example, you cannot put a breakpoint on this line in JDB and break here. It will not work. And the logic here is that it has a peculiar syntax. Accessor assembler is basically branching logic. So it checks the maybe weak ref, and based on what it is, it assigns one of the two variables. Either it is a lexical variable or a property cell. And the maybe weak ref variable comes from the feedback. Now from here, we can immediately conclude so that there is some corruption going on inside of the feedback vector slot, obviously, because the code takes out data from the feedback slot, and then it branches to if property cell, and apparently it goes to the place where assumptions are broken. And here, notice this function says get heap object assume weak. That this function internally doesn't check the type of the object. It assumes that it is a weak reference, but it turns out that it's not, which is why we're getting the type confusion here.
Alisa, may I ask you a favor?
Yes.
The font's a little bit larger.
Font?
Yeah.
I will try.
My eyes is horrible.
Okay, this is going to be a bit small to understand the context, I think. So from this analysis, we can conclude that there is a feedback vector corruption, basically. And so we start to think, okay, so this is a feedback vector corruption, how to debug it? And so we go to the next phase. Normally, when you start dynamically analyzing the exploits, you want to do it in the debugger. But this is not always the good idea. Especially in this scenario, many functions will be called dozens of times, and you just get lost in the debugger. So of course you can try, but for me, in this particular scenario, debugging just didn't work. And instead, what I did is I added some debugging logic inside of the V8. What I wanted to know, okay, I realized that the bug is somehow related to feedback vector corruption. So obviously I need to track how feedback vectors are allocated, filled, and changed. And then at some point I will see where exactly corruption happens and why. Also at this point, the debugging arguments also may be helpful. For example, we can find the D8 arguments which are related to feedback and check if there is anything of interest to us. And indeed there is an interesting flag, trace feedback updates, which can trace updates to feedback vectors. So let's try to run the POC with different arguments for introspection first. to try to gather more information about what is going on here. I will be using the original POC, and I will use a flag trace feedback updates and trace, okay, just trace feedback updates for beginning, just to see what it does. So if you just run it with this one flag, you can see that indeed it tracks feedback updates, but it tracks how exactly. It doesn't show here the uninitialized state. It shows which exactly slot it was. From the uninitialized state, it was updated to monomorphic with a specific call. But this is actually not very informative. It's just, for this vulnerability, it's not informative because I want to see what exactly is going on underneath. What else can I do? I want to trace garbage collection. That's -- trace GC. And okay, there is something a bit more interesting because we have a bunch of garbage collections happening in the middle of feedback updates. So this can possibly mean that this is the spot where our feedback slots were somehow corrupted. This is a very weak and random hypothesis, but it might work. First, there is the initialization of the feedback vectors, then there is multiple garbage collections because of the memory pressure that we applied in the POC, and then there is some additional feedback updates. This may be useful. What else can I try? I can try print bytecode, but it will print a lot. So this is a full output with print bytecode. Oh, it's not actually that large. Now this is already a little bit more interesting because at least here I see which bytecode was executed. It also says that it first generated the bytecode for specific function. It doesn't say which function, just with one parameter. Here's the bytecode for it. It may be just a global scope. Then it also another generated bytecode. There is quite a lot going on here. Also here, where it dumps some symbolic information, you can recognize specific names that you can find in the POC, our eval, the various variable names. Then there is this garbage collection happens, and once again there are some bytecodes printed, and then it seems like this output just breaking and we're checking again. So this is already a little bit more useful. It provides more information, but I still don't see what's going on here. But I already have a hypothesis that it probably must be related to this garbage collection phase, because obviously it breaks in the middle, and then there is some feedback vectors updated here, and after some more execution it just checks. So what I just showed to you is that you can do the initial research phase by using simply the introspection mechanism provided by the software. Of course, not all software has this kind of amazing facilities like V8, but V8 has a lot of this kind of flags, and as you saw, there is much more of them. And similarly, inside of the JavaScript program, you can invoke specific intrinsics like debug print, for instance. But I'm not going to use it here. And this first stage of introspection, it already allows us to gather a lot of information about the vulnerability. So what's next? I want to inspect what is going on. The next, once again, we can take a debugger and put some breakpoints. But once again, as I told you, in this vulnerability, it's extremely unsuitable for debugging with a debugger because the vulnerable functions will be called so many times. But normally, just to give you an idea of how it works, so I'm going to go back to the patch. And of course, I think that I will need to put a breakpoint on at least the most critical function, probably on all functions that are involved in the patched site. There's a few of them. Record declaration scope evil, record evil call, all that. Some of these functions are less relevant, so maybe I could try with a check to see what's going on. So anyway, if you try this, you will see that there are so many breaks in the debugger that it's useless, and it doesn't provide really any more new information. So instead, what we can do is we can add some debugging logic directly into the code of V8. And specifically, I wanted to investigate some points which I felt like were related to the vulnerability. I made a patch. Where is it? I'm just going to show you my patch and explain what exactly I changed in order to introspect in more convenient way. So this is my patch. It's quite a bit messy, please don't pay attention to that. It's just I prefer to receive a lot of information as much as possible, so there's quite a few updates here. First, there are some updates related to bytecode printing. And actually, without these updates, I think V8 doesn't print the bytecode at all, so you will actually need them if you want to introspect the bytecode. Especially V8 enable trace ignition and trace baseline exec. At least last time I tried, it required to change these variables to be able to print it. And then, so basic idea is that instead of putting a breakpoint in the debugger, I decided to add some debugging logic in the interesting points in the program. This is one of the functions that were involved in the patch, scope snapshot reparent. It logs when it enters the functions. It also here prints scopes because I have identified that the buckets related to handling evil in different scopes, so obviously we want to know more about this. Similarly, in this one, scope snapshot reparent, also we record the call itself, and we print the new parent. According to analysis, it seems like there are different stages in which the parsing happens, especially when parsing the arrow function. So, because arrow function can be easily confused with the parenthesis expression. It starts with a parenthesis. So if you look at the code, a code which parsing, it does it so linearly, symbol by symbol. So it goes parsing, 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 it finds the parenthesis, and it cannot really understand that this is an arrow function. So at first it just parses it like something that doesn't require its own scope. And it marks evil functions here as they belong to this scope of this function, the outer scope. And after the parser gets to the arrow, finally it realizes that it's an arrow and it updates some internal parameters. At this point, because it's an arrow function, it will require its own scope. And in the way how in JavaScript engine, in V8 it is implemented is scopes are structured like a tree. It's like, so this is the outer scope, the global scope. Then there is the function scope, and then there is the arrow function scope. They are kind of nested. But
That means you mean
at this point, it's just inside of the function scope, and the outer scope will be global scope. But inside of the arrow function, it's arrow function scope, then the function CCC scope, and finally the global scope. So they are nested. And during the parsing, because at this point the parser cannot recognize that there is a new scope here, so it just parses it like it belongs to this scope, to this function scope. And when it reaches this point, it needs to reparent this kind of the tree, which I'm trying to visualize. Now it needs to change the parent. So this eval calls will now belong not to the scope of the function CCC, but to the scope of the arrow function. What did you want to ask?
You mean global and some kinds of the scope, some kinds of confusion, or
Yes. Here it is actually related. It's a bit intricate details, because for eval, as we mentioned previously, the strict and sloppy modes, in strict and sloppy modes, variables are processed differently. So when eval is in normal mode, inside of the eval scope, it can access variables in the global scope. But if it's in strict mode, then it can access only local variables. So initially, during the parsing of this function first, it doesn't recognize that it's an arrow function. It thinks that it's still in the class scope, which is strict scope. And it thinks that eval must be executed only in the local scope. It cannot access the outer variable. And then, so it generates the opcodes which are related to accessing variables only inside of this local scope. And then it reaches this point, finally recognizes that this is arrow function, which requires its own scope. It reparents this code to the scope of the arrow function. And due to the bug, in this situation, the eval will be evaluated as sloppy. And in this situation, the bytecode will be able to access the global scope, and the bytecodes will be completely different. Now I'm going a little bit ahead in the logic of the bug. So I was showing you my login patch. Okay. Yes, I was explaining why I edit this logic particularly, because I wanted to track how exactly reparenting happens, reparenting of the snapshot, because I see that this is where the confusion happens during this or after this reparenting. Also, it's quite obvious from the patch itself. So I edit this logic. Another thing here, declaration scope deserialize receiver, some logic. I don't remember why is it relevant, but it's probably also related to this. Edit print in some scopes. Basically everything, all the functions that were patched, I want to see them in the tracing log, and also some additional functions that I identified as relevant. In addition to that, I'm printing here the scopes, and I'm printing here some notes about when specific variables are set. These variables that are found in the patch, and the variables that actually tell the engine whether or not the eval is in sloppy mode, or whether eval can access global variables or not. Another thing that I patched out here, this is my minimize test case, and it's checking here. So I just wanted to patch out this check in order to see what will go on. And because currently it checks and it prohibits me from seeing what is going on further in this. So this check will be patched out. But at the same time, I will print it in the log to know that a check should happen here. Also, obviously, I'm printing here the feedback vectors and metadata. And some information like length and size, because this was my main goal. If you remember where we stopped, basically I was looking at these dumps and I was thinking about this idea that it's related to garbage collection, that's between the feedback updates, and I'm able to see the bytecodes, but I'm not able to see what exactly gets updated in the feedback vectors. This is my main point of this patch. I wanted to print the feedback vectors to visualize it.
Can I say if I see some kinds of related to the feedback, then most likely related to the GC things, the garbage collection? You will see that in the debug logs, you will see some feedback problems or old space things that I could predict.
No, of course you cannot assume that.
Okay.
If you see some checks related to feedback vectors, it can mean anything.
Okay.
Actually, implicitly feedback is involved in every type confusion in optimized code. But normally we don't get checks like that, like feedback vector type confusion.
Okay.
This was the first time that I ever saw it.
Okay.
But of course, you cannot assume that kind of thing that is necessarily related to GC.
Okay.
There is some additional logic. Also here I wanted to track specific opcodes, for example load global, because I identified that there was some issue with it. So basically there is a bunch of things. I'm just going to show you how it will look like with all this tracing. I have a different build for that. So I'm going to trace the original POC. Okay, so this is very huge output, so it might take time to process it, but actually it's easier than it looks like, because I already have an idea of what is going on here. That there is some feedback initialization, then there is a garbage collection, then there is more feedback initialization, and somewhere in this spot corruption happens. So what I did from here is I put this output in a separate file and actually analyzed it. And at some point, of course, I started noticing some interesting things, which is specifically related to our crashes. So, okay, so this is the original proof of concept. This is the bytecodes. There is nothing interesting here. This is our first instance of initialization of feedback vectors. This is still kind of a passive phase where the engine just initializes things. This is our garbage collection happened. Okay, actually it was the okay, I'm just going to run it again because I'm confused with what I'm doing. Oh, this is the output which resulted in a check, and I want to look from the beginning and to see what's going on here. There is a lot of additional logic here. Most of it is not very informative, but it's still useful. It prints the scopes. There is the global scope. There is our function CCC. This is specifically the spots where it sets the metadata, records the feedback for specific feedback slots. You can see which slot has been updated and which kind is in this slot currently. Here we can see our feedback vector in a slightly different way. And now it starts processing the actual feedback vectors, which I showed you before. Currently these vectors are uninitialized, so it just created the feedback vector and put inside of it the bytecodes that it was able to obtain from the compiling. But the feedback is not initialized yet. And now you can see here some feedback updates, and here is how exactly these feedback updates look inside of the array. So feedback slot 3, this is it. It's set to eval call, and feedback slot 5 defined named own. So in this way I see already what I want to see is how exactly feedback vectors are initialized in the runtime. This is already some good information, but still I need to see why exactly it's corrupted. Here it continues along the same ways, initializing of the feedback vectors for each particular bytecode. And this spot is where garbage collection happens. So at this point I'm becoming aware that in the next pieces of log probably I already should be able to see something going on. And this already a little bit attracts my attention because the bytecode looks a bit different from what I saw before. I'm not going to go deeper into it. I just know that now garbage collection has happened and probably a feedback vector corruption is somewhere around. There is some scopes. And this one also is very suspicious because the bytecodes look a bit different than I saw before in the log. Because technically they shouldn't look different. And this is where finally I see the corruption. In slot number 9, you can see that this is where it was crashing. So at this point it's already corruption has happened. Because this is a bytecode of type call and the feedback must be an heap object which represents a function, but in this case it's a map. So it checks in the debug build here. In this way, so basically I have identified the specific spot where corruption happens. And indeed it is related to garbage collection. And here is our check. In this way I just reproduced the logic of the vulnerability in a more visualized way. So what goes on after here is we start analyzing even deeper, and I'm just going to go to the conclusions and explain what exactly did I analyze.
Alisa, I found that your hash, the release build of the commit is 323ADA. Is it the same as yours you were showing up to me?
What's again?
Because you sent me the release build of the commit, the hash.
Oh, yeah, No. I just mentioned it in the beginning of the workshop that actually I just realized today that my patch was based on a different hash.
Maybe you share me later on.
Yeah, sure.
Yeah.
But do
Yeah,
you,
yeah,
do
the
you really
hash
need
bar.
the patch? Because
No,
it's so
because
messy.
Not sure because the trace from my understanding the trace feedback updates is added later.
Oh.
So we cannot keep
Oh,
that,
so
keep the
internals
trace.
changed
Yeah.
or something.
No, it is a bit older. The patch, the one you were testing is
Yes, my patch currently,
latest.
the build that I'm using is from October, I think.
Yeah,
I
so
can actually.
So there's a discrepancy.
Yeah, it's October 26. It's just about 2 weeks before your build, so it's not really relevant. Do you think you need this particular build?
Yeah.
Yes?
You're right.
Okay.
Maybe
sure,
just
sure.
later it takes
Just
some
later.
time to build.
Just
Yeah,
later.
sure. I will.
Yes, just
I will
later.
send you.
Yeah,
But
because we got recording.
Generally,
we don't
I
repeat it.
only changed it because I needed to apply my own patch because it was based on
Yeah.
this.
But it's still good because we got some other things, then we have more detailed patch analysis. But we simply just repeat again. That it's all right for that.
So after analyzing all this, basically I took all this big log and started analyzing it. I already now have enough information after I started printing these feedback vectors, enough information to put it together and investigate in low-level details what is going on here. And also this situation, in the process of this, I kind of validated my hypothesis about what is going on here, that during the garbage collector, the feedback vector somehow gets corrupted, and it is related to evil, to confusion of evil strict and sloppy mode, and it is also somehow related to flushing of the bytecode. So I took this log and analyzed it, and I'm just going to show you some excerpts that were meaningful. So basically, I distilled the log into a smaller and better for analysis kind of dump. We need to observe a feedback vector specifically of the arrow function before garbage collection and after garbage collection. And here I can see that so here is some analysis notes that I wrote after analyzing this log. It was obvious that there was first some feedback metadata created, and then after during garbage collection the bytecodes were discarded, and so was metadata inside of the feedback vector. So remember that feedback vector has bytecodes information, which one slot, one bytecode, and metadata is the actual feedback which stores it. So what happens here is during the garbage collection, when bytecode of the function is discarded, it also discards the metadata, obviously, but it keeps the feedback vector. And the feedback vector still stays here with the same bytecodes. And because of the vulnerability in this code, the bytecode was actually changed during parsing of the arrow function. So the feedback vector became inconsistent with the actual what should be. And when the feedback vector started, when engine started filling the feedback into that old feedback vector, obviously there became, it put it in the wrong slots, and type confusion happened. This is something that I kind of hypothetically or theoretically analyzed based on these logs after analyzing everything and putting together.
Because they put the wrong slot, right?
Yes, yes, yes,
because
exactly.
the the scope
Mhm.
related to this one.
And specifically, yes. So first idea I got that because when the bytecode is discarded, the feedback vector stays the same, and the engine does not think that does not assume the bytecode to change. It's like not normal.
Mm.
When you have one bytecode and suddenly after second recompilation it becomes another bytecode, it's not normal.
Mm.
It's only due to the bug, and because of that, the feedback vector is trusted. It thinks that it will always have the same structure with the same bytecodes. And when it puts the metadata, it doesn't correspond to the type. So it expects some metadata, but it's a different metadata. So the general idea is this. And after this, of course, we can go deeper and analyze why exactly does it put a wrong metadata. And this is where actually it is directly related to eval, sloppy versus strict. When eval processes variables in a strict mode, it will fetch them in the global scope, and it's one bytecode. And when eval executes in sloppy mode and fetches variables from the global scope, it's a different bytecode. So internally, there are bytecodes that start with STA and LDA, which correspond to storing and loading. So when we take a variable, it uses a LDA variable to fetch it. So there is an LDA global, for example. I think it's a bit differently named in the engine. LDA load global. Нет, LDA global. You can see in the bytecodes.h there is the full list of bytecodes which exist in the V8. And basically it's the primitive operations that can be executed. And LDA global is specifically loading a variable from a global scope. So the way how it is related is because of this difference. When eval was considered to be in the strict mode, engine generated a bytecode for local access. But when it was once again parsed and identified as in sloppy mode, it generated additional bytecodes to load variables from the global scope. And it looks like here is an example of the old metadata and the new metadata. So before garbage collection, this is the correct feedback vector, which has 3 calls here. And after garbage collection, after reparsing, after identifying the error function, it identified that eval should be executed in sloppy mode, and there are additional bytecodes where load global not inside typo, which tells the engine to, instead of looking up in the local scope, to look into the global scope. And because these additional bytecodes were added, it shifted the feedback vector a little bit. You can see that in the original feedback vector there is only slot 1, which has load global primitive. And then after the garbage collection and type confusion, there are 2 additional opcodes in the slot number 7 and slot number 13. But the feedback vector is the same. So this is feedback metadata, but the feedback vector is the same and it corresponds to this. So for example, here in slot number 7, in the original feedback vector, it has the call bytecode, which accepts a weak pointer as a type of feedback. But after garbage collection and reparsing in the slot number 7, there is a completely different opcode. While the feedback vector is still the same, but the type of feedback would be related to load global. And it will accept a map or some other type of feedback, which is why this type confusion happens. Because of its shift and wrong type of feedback here. So this is basically more or less the idea of this vulnerability after completing the initial stage of analysis. At this point, I have more or less semi-detailed and more or less complete understanding of what is the vulnerability. And the only problem is that it looks completely useless, because the confusion of a feedback cell, it's not possible to confuse because it's so deep internals in the engine. You cannot do anything. So at this point, I will need to actually investigate further and generate ideas to how it can be exploited. The stage 3 is done, and I'm going to close this workshop soon on this. So just to say what was my idea. So the next stage is exploit development, and in order to do this, first thing I need some useful primitive. Obviously, a type confusion in a property cell and feedback cell is useless. So at this point, I didn't have more time to develop the exploit, but I had the idea: what if I could manipulate this feedback in such a way that I am able to confuse specific bytecodes here. So here, in this situation, what we have is that a slot number 7 call is type confused with a slot with load global bytecode, which is why the type confusion is not exploitable. They are very deep internal objects that I cannot do anything. But what if I could actually use some different bytecodes, and maybe one bytecode that uses a map and another bytecode which also uses a map. But because they will be type confused, there will be no check, and maybe I can just change the map. And from here, I go directly to modification of the object like normally. This was just a rough idea, but unfortunately I didn't have time to write the exploit. So I just shared it on Twitter with JJ.
Yeah. He's right now watching on you. We share in the friend groups. You can say hi to him.
So yeah, I shared the idea, and he actually did it, which was great. He was able to implement this idea, and he made the proof of concept, which confused a different type of bytecode, which is more suitable for type confusion. To go away from this stupid confusion of feedback cell and to something more useful. And after that, having his proof of concept, Jack Wren developed a full-blown exploit, which was also a very nice work. So yeah, this can be left as a homework to look deeper. Basically, I want just to outline the further steps of exploitation. First, of course, we need, as I said, a good primitive for exploit development. Here, this type confusion is not a good primitive, but I had an idea of how to make it, and it turns out to be a good one. So first we need to change the state a little bit to get a good primitive for corruption. Then we need to convert the state corruption to a maximal powerful exploit primitive. We will try to achieve arbitrary read-write, if possible. It's not always possible, but it's our ultimate goal. So we need to manipulate the state. As I said, if we're able to confuse one object map with another object map, it is straightforward. We just get an object which access out of bounds and game over. But the general idea is this conversion from state corruption to maximal powerful primitive. And from here it goes pretty much in the standard route. We will need to build the next level primitives for JavaScript engine exploitation, such as getting the object, the address of the object, and faking object, and finally using it to achieve arbitrary code execution in the sandbox. So this is the general outline of the exploit development, which is out of scope from this workshop. So that's it.
Yeah,
If you
thank
have any
so much.
questions, please.
Yeah, first of all, I'm thankful to Alisa. You come to make a really concentrated, concentrated workshop. And also, later on will get you your hash, and even if you can share with us your analysis or patch the files with us, among us. And the recording we will also need to be repeat again, okay? Because I think makes me think about how to systematically to do the patch analysis to identify the trace, the root cause analysis the RCA is really awesome for this. Before that, the RCA we just learned by ourselves. I just learned by myself, so it's not really complete. Especially when I see the code, how to check and trace and manipulate those different threads in the shell is very important to understand the debug trace. So this is really helpful to me for this part especially. Yeah.
I know, systematic approach is everything. In my training system, it's all about methodical and systematic approach to everything. And including be it exploit development or patch analysis, I always think in frameworks and of course I started, if somebody read my FRAC article, in the FRAC magazine from 2014, I think it was quite a bit ago, and it was such a silly exploit, like so ad hoc.
Yeah.
It's like beginners normally think like this. They stumble into a problem, they find the first solution to it, go a little bit further, find some solution, go a little bit further, like this ad hoc development. And the problem is that on each step you lose determinism. Your exploit starts to make more and more mistakes and more crashes. So when you finally get to the final point, your exploit is unusable if you go along this route. And also, of course, you can be using some bad primitives or something. And which is why exploit development for me is very systematic art. You have to set up the platform and think in frameworks in order to put things together like a normal builder, not just putting some scripts together.
As I know you have the online training or also on exploit development. Can you introduce a bit about you have it?
Yes, actually, I have a two-part series on exploit development. So basically, exploit development consists of two parts: zero-day vulnerability discovery and then actual exploit development. There are two different things. And as you mentioned recently, finding vulnerability is very different from exploiting it. It's like two different worlds, which is why I decided to split these things apart and make two different trainings. So the first one, zero-day vulnerability research, is all about the methodology, the system of how to find vulnerabilities, how to do threat attack surface mapping, a little bit of everything, what do you need, and so on. And the second part is all about exploit development. So this is basically what I showed in this today's workshop, the kind of systematic approach to exploit development. And especially is focused on binary exploit development, which is universal and doesn't depend on specific operating system or software. For example, the things that I speak here, they are a little bit specific to JavaScript engines, like achieving arbitrary read-write. But normally, there is some concepts that are universal across all operating systems and all softwares, like types of exploit mitigations, types of vulnerabilities, types of exploit primitives. They're universal, and this is what is the focus of this training. It's called binary exploit development, and I just planned it for next year and recently posted a description in my Twitter.
Yeah, at least have a follow-up and to follow-up session and to move along the ladder.
Yes, definitely. And these are basically, they are a little bit more for beginners. So what's today is the specialized stage. So normally first you learn the basics, finding vulnerability and general exploit development, and then specialize on JavaScript engine, for example. So today is a little bit more specialized, even though I try to explain in simple terms, but generally it's more specialized material. And for binary exploitation and finding vulnerabilities, I want to make it beginner friendly, but also comprehensive to include all the necessary information.
Okay, any questions for Alisa? Feel free to ask questions via small class. And anything you think is really difficult, looks like difficult or challenging or still not speak up, no problem. I also ask questions.
I think it's just to your experience, like usually how long an exploit can be developed, like go through all these process we just walk through. Usually, is there like an average time, or usually it's just like you check those stuff on, and then just somehow discover that vulnerability and start moving on that part.
It depends on the specific scenario. Basically, there are two extremes. There are exploits that are very templated, very common. It's like basically copy-paste,
Yeah.
in a little bit advanced copy-paste. And then there are exploits that are novel. They require novel technique and novel research. So this vulnerability is on the second
Yeah.
extreme. And of course, there are different stages in between these two extremes. So for a very basic vulnerability, an exploit can be developed under 1 week. Even if it's a complex exploit, even for something complex, but if you know how to exploit it, you just sit down and put the things together. And 1 week is all it takes to make a good, reliable exploit, not something just put together. And on the other side, if you have a very advanced exploit, then it can take anywhere from 1 month and up. But I think that a couple of months would be somewhat median. And obviously, it is not a straightforward process. Usually you would be, sometimes you can put it back and go do something else. Sometimes you can kind of walk around it, collect information, because when you have situation like this one, the process that I tried to show you is how we are able to collect information from different sources. Then you put it in your mind and put together the mental model, and after that you finally see the next step. The problem with this kind of exploits, you never see the next step before collecting a lot of information from different sources. So that's the problem, and this is why I think this process for non-trivial exploits, it looks like really spread out. Maybe you will go and do something else, and meanwhile your mind keeps processing the information. That's what's happening in the background.
Yeah, I'm okay. But I will watch your video again, repeat again.
Maybe a question for me. If I'm starting out, because this session is I'm still digesting the information, it's kind of hard for me to grasp everything. So, what would you suggest to be my next step to dive into this topic? Do you recommend case studies or any specific topics to do research on, like how the V8 engine works? What kind of resources would you recommend?
The most useful thing you can do is analyzing vulnerabilities, known vulnerabilities. And if you're able to find a write-up of an exploit, absolutely read it. Normally in this area, there are not many good write-ups and not many exploits, so normally we will need to analyze the code. But your first step, because the blogs are available, read them all the blogs, all the write-ups. Then go to actual vulnerabilities. When you have exhausted all the blogs, start analyzing the security patches and vulnerabilities. So when you cannot find the write-up for vulnerability, you will need to analyze the patches in the same way as I discussed in this workshop. Just whenever a new Google Chromium update comes out, you can take any bugs that you like, find the patches and analyze them. This is what we usually start with. At some point, you will feel some confidence that maybe you have enough information and knowledge to try and develop exploit for V8 CTF, for example. It's not a 0-day, but it already can give you some bounty.
So, based on you just show us, we can see a lot of different CVEs, and are all of these exploitable or meaningful to exploit?
It depends. Actually, a CVE, of course, is not guaranteed. Generally, CVE doesn't guarantee anything. It can be absolutely useless bug. But generally, in Google projects, CVEs are good. Especially in V8, if you see CVE in Chromium or V8, most of them, I would say, at least deserve your attention. And even if it is not exploitable, it is very important that there are some classes of bugs that maybe are not exploitable or not convenient for some reason, but they still can give you some hints and some valuable information about where new bugs can be found, what primitives can be used. So For V specifically, I do recommend to analyze all the patches as you can, as much as possible. And you will be gradually learning and understand which patterns are there. And of course, at the same time, you will be looking at the code base and maybe, going laterally and start finding some bugs in the process.
That's good, Alisa. Then we should end here. I suppose it's really concentrated. We don't need a lot of time about it. But we're thankful to Alisa, okay? Thank you. Thank you.
Thank you.
Yeah. Okay. 1 second.亦都係野豬關注組嘅主席。
哦，我哋都同心成立多嘅，
呢啲都影，
係啊，
幫手
乜都
影啊！
乜都撈。
KJ 幾時到啊？
所以
聽日。
Yeah, sure. Okay, I'm not sure.
Oh, okay.
Can you?
Let me make it.